Okay, so we're starting section 3.3 now. So we'll start with problem number 1. And what we're asked to do is rewrite each statement using the if-then connective. Rearrange the wording or add words as necessary. So number 1 is you can believe it if you see it on the internet. You could think of it in 2 ways. If you believe it, then you can see it on the internet, or if you see it on the internet, then you can believe it. I prefer the second one. So let's just write that down. If you see it on the internet, then you can believe it. And I'm looking at the solution manual. And there's 2 ways. You can believe it if you see it on the internet, or if you see it on the internet, you can believe it. So either one's is really okay. Number 4, all perfect square integers have units digits 0, 1, 5, 4, 5, 6, or 9. So you could say if a number is a perfect square, then the units digits are 0, 1, 4, 5, 6, or 9. And actually, it says integers, I guess. Yeah, an integer. Okay, let's look at number 7. Number 7, no pandas live in Iowa. So you could say if you're a panda, I guess 2 ways. You say if you are a panda, then you do not live in Idaho. Or you could say if you live in Idaho, then let's see, no pandas live in Idaho. If it is a panda, I guess that's better because we're not. You are a panda. So if it is a panda, it does not live in Idaho. Okay, so we got next 10. Running Bear loves Little White Dove. If you are Running Bear, then you love Little White Dove. Okay, let's see what the book says. If he is Running Bear, then he loves. I guess it's the same kind of, I'm using more like if I'm Running Bear, but if it is, if he is, whatever. Same idea. Okay, the next one is 13. So what we're supposed to do is decide whether each statement is true or false. So 13 says, if Q is true, then P intersect Q is true. So it's kind of like if you got 2 if-then statements within each other. But if you remember the truth table for conditional, if we say Q and we have P, it really doesn't matter the order we put it in. Well, I guess we'll do it in the right order. So we have P and Q. And so P can take on either true or false. But Q is always going to be false. It is always going to be true. So Q is true. And so it says, and if you do the intersection of these two, so the intersection of P and Q, you get true and you get false. So, and then this part is the conditional. We have Q. So true, Q can be either true or false. And the only time this conditional is false is when this is true and this is false. So since these are both true, that's going to be true. And because it's false, false, then that's also true. If you remember back to the table. So what we're looking at is this, that, then Q. So this, we look at these two columns to determine that. And if it was false, true, then we would, actually if it's true, false, because if we have a false here in the first term, it doesn't matter what the second term is because we really have no way of checking it. It's kind of a weird way of doing it, but let me make sure here. The statement if Q is true, then P and Q, then Q is true, since with a true consequent, the conditional statement is always true. And even though the antecedent may be false. Oh, actually, yes, Q is true, so actually I need to put that to true. So it's saying that if the second term in the if then is true, then it's always true. False, false was also true, but I forgot to reflect this part. So this is always true. This is always true. So when I do these two together, and I'm using the intersection, this is true and this is false because you have to have both truths to have a true result there. And then we compare these two, and because these are both true, the second term is true, then it's true. The only time comparing these two columns using this connection is false is when this is false, this is true, and the second one's false. Okay, we'll do one more in this section, 16. The statement, if it flies, then it's a bird, and it does not fly, or it's a bird, are logical equivalents. So let's say P is the statement, it flies. And let's say Q is I'll believe it. So the first is P, then if P, then Q. The second one is if pigs don't fly, so that's if pigs don't fly, then I won't believe it. I know those equivalent statements or not. And I'm just trying to think here if you, just looking at it logically, if it does not fly, if it flies, then it's a bird. It does not fly, or it is a bird. Oh, okay, there's an or I forgot there. I don't know why I did that. So I think there's some equivalent thing here. So this is or. So let's try again. It flies, then, oh, I'm looking at the wrong problem here. What am I doing? 16, okay, sorry. If it flies, then it's a bird. Oh, no wonder I'm looking at the wrong problem. Let's try it again. I think I was looking at two problems, but yeah, I was looking at the wrong problem here. If it flies, then it's a bird. If it flies, it's a bird. Okay, so that's what that is. And then the second statement is, it does not fly, or it's a bird. So that's what we have. So if we go back to these equivalent statements in the book relative to negation, says writing a conditional as a disjunction. So it says writing a conditional P then Q is equivalent to not P union with Q. So I think it's true. But it is true. Okay, so that is true because we're using, if you go back to page 105, you'll see that there's that equivalence. And that's what we have in this particular case. So let's look what it says in the book. Statement, if it flies, then it's a bird, and it does not fly, or it's a bird, are logical equivalents. To decide if the above is true, examine the corresponding truth tables for each individual statement. So you can do that. Then the book already did that. That's how they came up with that particular equivalence. We're writing the conditional as a disjunction. So yeah, why don't we actually do that? So let's do the truth table. If you get the same result, then you're okay. So let's just make something up here. So we're going to have a column that's P and a column that's Q. And then we have all the combinations: true, true, false, false, true, false, true, false. And if we do P then Q, these are true except for this one right here. That one's false, that one's true. So that's just from the book. And then if we do not P is false, false, true, true. And so if we take not P union with Q, so that's this one with that one. Union means if one of them's true, then the whole thing's true. So true, false is true. False, false is false. True, true is true. True, false is true. Since these two have the same result, in terms of the truth table, given the same P and Q combinations, then they are equivalent to each other. So that's another way of looking at it.